All right, hello everybody. Today we're talking Objective 2 of the Geometry B review, right triangles and trigonometry. Okay, two very important topics, two things that are going to show up for you a ton as you go through the rest of geometry, as you go through the rest of your math classes. Okay, and also in the real world, there's a lot of different situations we can break down into right triangles and do problem solving with what we're going to show you here today. So let's rock and roll here. All right, so the first big thing we're going to talk about with right triangles is the Pythagorean theorem. Okay, good old a squared plus b squared equals c squared. And it just says that for any right triangle, the sum of the squares of the lengths of the legs is equal to the square of the lengths of the hypotenuse. Okay, so if I have a right triangle where we have the hypotenuse across from the right angle, and my other two sides are the legs, okay, then the leg squared plus the leg squared is equal to hypotenuse squared, meaning that the A and the B are the legs, and C is the hypotenuse. All right, so let's go ahead and show you how to use the Pythagorean theorem. Problem 1, part A says, what's the length of the hypotenuse of triangle ABC? Okay, let's call that hypotenuse just x. And anytime I have a right triangle and I know 2 out of the 3 sides, I can always solve for the third side using Pythagorean theorem. So we want to use our good old a squared plus b squared equals c squared here. Okay, where the a and the b are the legs, the 20 and the 21. Now it doesn't matter what order we put those in. I'm just going to say 20 squared plus 21 squared. Okay, and then the c squared is always my hypotenuse. So instead of saying c, we'll just call that x. Okay, so equals c squared. Once I fill the Pythagorean theorem in, I've got a fairly simple equation that I can use to solve for x. I'm going to square things out first. 20 squared I know is 400. Okay, plus 21 squared is 441. Okay, we can combine those. 400 plus 441 is going to be 841. And then to get the x by itself, I want to get rid of the square root. So what I'm going to do is I'm going to square root both sides of this equation. That's going to leave me with just an x on the right side, and the square root of 841 is a 29. Okay, so I know my hypotenuse is 29. All right, that's how you can use the Pythagorean theorem to solve for a hypotenuse of a right triangle. Okay, part B of problem 1 in your note guide is the same idea. So take a minute here, pause the video, work your way through part B, ask any questions if you got them, and then before you move on, before you hit play again, throw a hand up in the air, get your answer checked. Let's make sure you're good with this stuff before we move on to the next problem. All right, problem 2, we're using Pythagorean theorem once again. And again, we're solving for x. Now notice this time, x isn't my hypotenuse. It's one of the 2 legs. So we're going to use the same a squared plus b squared equals c squared equation. And this time when I fill it in, the x is going to be on the left side. So we could say x squared plus 8 squared is equal to the hypotenuse, the 20, on the right side. Okay, the big thing when you're setting up Pythagorean theorem is get stuff in the right place. If you put the hypotenuse in the wrong spot, you're going to get the wrong answer, so pay attention as you're setting things up. Okay, so at this point I've got a, again, pretty simple equation to solve. Let's square things out. So we've got x squared plus 8 squared, which is 64, is equal to 20 squared, which is 400 again. Now this time to get the x by itself, I'm going to subtract 64 from both sides of the equation, which will give me that x squared is equal to 336. And then once again, we'll take a square root to get the x by itself. My pen just got goofy on me there, so square root to get the x by itself. And that's going to leave us with x is equal to, we'll just say an 18.3 when I plug that square in my calculator. Okay, we're not going to worry about any radical form or anything like that here. We'll just round it to a decimal place. Okay, so there's an example solving for a leg of a right triangle using Pythagorean theorem. Okay, once again, in the note guide, go ahead and pause the video, work through problem B, raise your hand to check the answer before you press play and move on. All right, next thing we're going to do is apply the Pythagorean theorem to some real-world situations. Okay, like we said, a lot of right triangles show up in the real world that we can use to solve for different stuff. Part A says, Jamal leans a 12-foot long ladder against the side of the house. Okay, the base of the ladder is 4 feet from the house. To the nearest tenth of a foot, how high in the house does the ladder reach? Okay, now this is really the same kind of math as we had in the last two questions. The big difference here is that we have to set up our triangle on our own. So I'd recommend draw out a picture. So we have a house, and we're leading a 12-foot ladder against the side of the house. And it says the base of the ladder is 4 feet from the house. Now, anytime in a story problem when you see the base word, you're thinking along the ground. Okay, we want to know to the nearest tenth of a foot, how high in the house does the ladder reach? Okay, that's the x here. We want to know how high up can we get. Okay, can we get to that second story window? Can we reach the roof? And the trick for this one is we'll assume we're using a right triangle. Okay, we'll assume that a house is coming out of the ground at a right angle. Okay, so once again, I can use my a squared plus b squared equals c squared to figure out what that x is. Okay, so I'm going to set this up as x squared plus 4 squared is equal to 12 squared. Okay, again, make sure you get the hypotenuse in the right spot. Right angle points to the hypotenuse. Hypotenuse is always my c. Okay, so I can square this out to get x squared plus 16 is equal to 144. I'm going to then subtract 16 from both sides of the equation. That'll give me that x squared is equal to 128. And then again, don't forget to take a square root on both sides. Pen doesn't want to do square roots for some reason here today. And that's going to leave us with x is equal to square root of 128, 11.3. We can say feet. We'll get 11.3 feet up the ladder there. Okay, so there's an example using Pythagorean theorem applied to a real-world situation. Once again, take a minute, pause the video, work through part B, and then get your answer checked before you move on to the next question. Next thing we're going to look at is the converse of the Pythagorean theorem. And what that's going to do is give us a way to classify triangles based on how they relate to that a squared plus b squared equals c squared. Okay, so I'm going to say that if the sum of the squares of the lengths of the legs of a triangle is equal to the square of the length of the hypotenuse, okay, so in other words, if a squared plus b squared equals c squared, then the triangle is a right triangle. Okay, so we've been dealing with right triangles. We know that's true with right triangles. So what I have with that statement is a way to check and see whether or not a triangle is right. Now I can take that a step further by taking a look at if it's not equal, what happens when the c squared is greater than or the c squared is less than a squared plus b squared? Well, if the square of the length of the longest side of a triangle is greater than the square of the lengths of the other two sides, so in other words, if c squared is greater than a squared plus b squared, then the triangle is obtuse. Now that makes sense because if I start with a right triangle, if I make C longer, that right angle is going to have to get bigger. It's going to have to become an obtuse angle to kind of compensate for it. And then in the other direction, if the square of the length of the longest side of a triangle is less than the square of the lengths of the other two sides, then the triangle is acute. Okay, so if C squared is less than A squared plus B squared, we have an acute triangle. Because again, if I start with a right angle and I make that hypotenuse smaller, that right angle is going to have to shrink and be acute. Okay, so if C squared equals A squared plus B squared, we have a right triangle. If C squared is greater than, we have an angle that's greater than a right angle and an obtuse triangle. And if C squared is less than, we have an angle that's less than a right angle. We have an acute triangle. All right, so let's go ahead and practice using those kind of classifications. Okay, problem 4, part A says a triangle has side lengths of 6, 11, 14. We want to know, is it acute, obtuse, or right? All right, so what we'll look at then is A squared plus B squared, and that's just going to be the smaller two sides added together. So in this case, that'll be a 6 squared plus 11 squared. When I do that, I end up with a 157. Then we'll look at C squared, which is 14 squared, which is 196. Okay, so the two are not equal, so we know it's not a right triangle. And what we just showed is that C squared is greater than A squared plus B squared for these three lengths. Okay, if C is bigger than, that means we're looking at an obtuse triangle. All right, if C was less than, we'd have acute. If it's greater than, we have an obtuse triangle. All right, once again, part B is just another example doing the same thing. Why don't you take a minute, pause the video, run through that one, and then check your answer before we move on. Now, the next thing we're going to talk about is trigonometry. And trigonometry deals with trigonometric ratios. These are equivalent ratios of corresponding sides of similar right triangles. So essentially what we're going to do is we have the sine, cosine, and tangent ratio. And by using our calculator, which knows what the values of each of these ratios are, we'll be able to solve right triangles, okay, using those ratios, using the calculator. Okay, we have three trig ratios, sine, cosine, and tangent. And for each of these definitions here, we're referring to angle A. And the way we talk about our triangle is going to be determined by which angle we're looking at. Okay, for angle A, I'd say that little a is the opposite side, B is the adjacent side, and C across from the right angle is the hypotenuse. Okay, so then our definitions are going to be sine is the length of the opposite divided by the length of the hypotenuse. Cosine is the length of the adjacent divided by the length of the hypotenuse. And then tangent is the length of the opposite divided by the length of the adjacent. Okay, again, the calculator knows what the ratios are for any angle I plug in, and then what I'll be able to do is solve for missing side lengths, okay, based on the sine, cosine, and tangent of those angles. All right, so let's start off by just practicing using those definitions here. Okay, you will have a simple question on the test where you just have to simply find the fraction based on which ratio we ask for. So for example, in this one, it says, what is the sine of t? Well, t is this angle right here. And our sine ratio is just the opposite over the hypotenuse, length of the opposite over length of the hypotenuse. Okay, and in this case, the 8 is the opposite side. It's across from the t. And the hypotenuse is always across from the right angle. So we have our op and our hyp. So I could say that the sine of t then is just equal to opposite over hypotenuse the 8 over 17. Okay, it doesn't really help us solve anything. Again, this is just working on using those definitions here. Okay, let's do one more together. B, what is the tangent of angle G? All right, so we're switching up our angle we're talking about. And as far as G is concerned, 15 is now the opposite side. 8 is the adjacent side related to G. Okay, 15 is across from the G. 8 is next to it. And if I'm talking about my tangent ratio, tangent is opposite over adjacent. So we could say that the tangent of G is the opposite 15 over the adjacent 8. All right, again, do pay attention to which ratio you're using and then also which angle you have. That's going to determine which side length you're dealing with. All right, so let's go ahead and actually use the trig ratios to solve for parts of triangles. And we're going to run through a part A and B here and show you some differences with the way these can work out. For both of them, we want to solve for W. And here's the process. 54 is the angle I'm going to use to solve for W. And what I need to do is decide which of these trig ratios I want to use. Suppose we pull this up here for now. Okay, the W that I want is opposite to my 54. And the 17 is across on the right angle, so 17 is the hypotenuse. What I want to do is I want to pick the ratio that deals with both the opposite and hypotenuse. Okay, opposite hypotenuse, that's my sine ratio. Because if I pick the right one with the sides I'm dealing with, I'll be able to fill in the equation so I can get the missing variable. Okay, notice both the cosine and the tangent have the adjacent involved. I don't care about the adjacent side. I don't know it. I don't want to know it for this question. That's why I'm using the sine ratio. Okay, so let's fill in what we know. We've got the sine of angle A, which is 54 degrees, is equal to, it says, the opposite on top, which would be the W, over the hypotenuse on bottom, which is the 17. Okay, so I have, again, a fairly simple equation that I can solve for W with. So for this one, I'm going to multiply both sides of this equation by 17. Because what I want to do is I want to cancel this fraction out. I want to make the fraction go away. So that leaves me with just a W on the right is equal to 17 times sine 54 on the left. And when I get the variable by itself, that's where I'm going to go to the calculator. Let's pull that up for you here. And it's actually pretty simple to plug in. We'll just make sure we're all okay with this. So what I'm going to do is I can go 17 times sine 54. Okay, the sine, cosine, tangent are just going to be 2 above the 7, 8, 9. I'll hit sine 54. Close parentheses. And when I hit enter, I get a 13.8, we can say, if we round to the nearest tenth. So we can just say our answer is equal to 13.8. All right, let's walk through one more of these here. Okay, again, first step's going to be to identify the sides we're dealing with based on this angle we're given. Okay, the 1 is my opposite to my 28 degrees. W is the adjacent. Okay, and then the hypotenuse is the one I don't care about for this one. So we're dealing with opposite, adjacent. That is the tangent ratio here. Okay, tangent of the angle is equal to the opposite over the adjacent. Okay, filling things in, I've got tangent of the angle 28 degrees is equal to opposite the 1.0, over the adjacent, the W. And then notice the big difference for this one is in part B, my variable's on the denominator. It's on the bottom of the fraction. So the way I solve it's going to be a little bit different. I want to clear that fraction right away once again. So this time I'm going to multiply both sides by W. Okay, because W divided by W cancels out. So then I have the 1.0 on the right side equals W times tangent 28 on the left. And I still don't have W by itself. So the next thing I'm going to do is I'm going to divide both sides by tangent 28. Okay, just like if I had W times a 7, I divide both sides by 7. Here, the tan 28 is just some ugly number. Not sure what it is, but I know when I divide it by itself, it cancels out. So that's going to leave me with W is equal to 1.0 over tangent 28. Which, once we get the W by itself, we'll go to the calculator, pull that up, slide that over here. And the way I'd plug this one in is just the way I see it. We can say 1.0, divided by tangent 28. When I plug that in, I get a 1.9 we can round that to for my value W for this one. All right, so those are the two different ways our trig problem solving for side lengths can work out. It either turns into multiplication at the end or division, depending on whether that variable is on the top or the bottom of the fraction. Okay, there's a part C in your note guide. Why don't you take a minute, pause the video, run through that one, and then check your answer before you move on. Next thing we're going to do is show you how you can use trig to solve for a missing angle in a triangle. So here it says, what is the measure of angle x to the nearest degree? So x is the angle I'm dealing with. And then for this one, the signs I'm given are the opposite side and the hypotenuse. Okay, and anytime I have two sides of a right triangle, I can solve for an angle using trigonometry. Okay, which ratio is that? Opposite hypotenuse, that's our sine ratio once again. So I'm going to fill that in. I know that sine of angle A is equal to opposite over hypotenuse. Okay, what do I have here? Well, sine of the angle I don't know, that's my x, that's my variable for this one, is equal to the opposite, which is the 6, over the hypotenuse, the 10. Okay, then anytime I'm solving for an angle, what I can do is I can just say that that angle x is equal to, since this is a sine, I'm going to go sine inverse of my fraction, 6 over 10. Okay, if I had cosine as the ratio I was using, I'd go cosine inverse. If I had tan, I'd go tangent inverse. This will be what I plug into the calculator. Now, you don't need to show these steps, but technically what you're doing is you're getting the x outside of the sine function by doing the sine inverse, which is just the opposite of sine. It cancels it out, it leaves just the x there. And if I do something to one side of an equation, I've got to do it to the other. That's how I'm getting the sine inverse of 6 over 10 on the left. Okay, again, you don't need to show those steps. You just need to be able to plug these in. And the way I'll do that, the way I'll get a sine inverse is I'm going to hit the second sine button. That's going to give me this superscript, the -1. And then I can just go 6 divided by 10. Hit enter. And to the nearest degree, we could say this is x equals 37 degrees. All right, part B is another solving for an angle using trig question. Okay, using our inverses once again. Okay, again, pause the video, work through that one, and make sure you check your answer before you move on. All right, last thing we're going to do is use trig to solve a real-world question, and that's going to deal with something called an angle of elevation. Okay, let's say you sight a rock climber on a cliff at a 32-degree angle of elevation. Your eye level is 5 feet above the ground, and you're 1,000 feet from the base of the cliff. What's the approximate height of the rock climber from the ground? Okay, a picture would be nice for this one, so let's draw one out. So we have a cliff. There's you, and there is a rock climber climbing up the cliff. And it says you sight the rock climber at a 32-degree angle of elevation. Angles of elevation are angles from the ground looking up. So that means that from your eye level to the climber is 32 degrees. All right, it also says that your eye level is 5 feet above the ground. So in other words, distance from your eyes to the ground is 5 feet. We'll show you how to account for that in a few minutes. And you're 1,000 feet from the base of the cliff. So distance from you to the cliff is 1,000. Once again, when you see this base word, you're thinking along the ground. And we want to know what's the approximate height of the rock climber from the ground. Okay, so we'll call this height here Rx. All right, again, we'll assume this is a right triangle. And as far as the side lengths go, if 32s are angle in this left side of the triangle here, the 1,000 is the adjacent side of that angle, and the x is the opposite side. Okay, opposite adjacent, that's my tangent ratio. Tangent is opposite over adjacent. Okay, I'm not going to pull those definitions up, but that's what the tan is. So I can set this up as tangent of 32 is equal to the opposite x over the adjacent 1,000. And then I have a simple equation I can solve for the x. We'll multiply both sides of this by 1,000. Okay, that's going to leave me with x is equal to 1,000 times tan 32. I can plug that in my calculator, which is going to give me a 624.9 feet, we can say. Okay, now the last step with this one is we just found that this x, this distance from the top of the cliff to our eye level, is the 624.9. What we need to do still is we need to account for our eye level here. We didn't add this extra height in, this 5. So that's where I can say the actual height is equal to the 624.9 plus a 5. In other words, 629.9 feet off the ground. All right, that's the trick anytime you're dealing with an angle of elevation, is you need to account for how high off the ground you're measuring for and then add that in at the end. Don't forget that last crucial step. Okay, that's it for our trigonometry objective. Okay, right angles of trigonometry objective. Start working on the Math Excel. Make sure you're going through that. Make sure you're getting help. And we'll see you folks next time.